Hello everyone, welcome to Dr. B.R. Ambedkar Open University. Today we are going to explain mean values theorem. So it is the inter part of the differential calculus and BSc first semester. So in my mean values theorem, today we are going to discuss about the Rolle's theorem. So this is a very important. In the exam point of also there is a one of the compulsory question from that mean values theorem. So in this mean values theorem we are going to discuss about that today Rolle's theorem. So let first of all see what is the statement. So in the examination also they will ask state and prove the Rolle's theorem. So we need to write the statement and we have to write that proof also. So first let's see the statement. What is the statement means? If a function f map a comma b to R is such that the first condition that f is continuous on the closed interval a comma b and f is derivable in open interval a comma b, and the third condition f of a equal to f of b, and these three conditions, then there exists a real number c belongs to open interval a comma b such that f dash of c equal to 0. See, let us observe here, f is continuous on closed interval a comma b and f is derivable on open interval a comma b and f of a equal to f of b, and there exists a number, one number the c in between of what is that a open interval a comma b such that f dash of c equal to 0. So this is the statement of the Rolle's theorem. Now let us go to the proof. So already in the condition 1 here they given what is that f is continuous, no. So every continuous function is a bounded. So what is the meaning of bounded? It has a infimum and it has a supremum. It has bounded above and it has a bounded below. So here f is continuous and similarly that is f is bounded and it attains bounded, that means it has infimum and it has a supremum, and previously you know what is the infimum and what is the supremum. So f is bounded and it has a bounded in a comma b, then there exists one more two numbers c comma d in a comma b such that f of c equal to capital M and f of d equal to small m. Here that capital M is that supremum and the small m is infimum, and we know what is the supremum and what is the infimum. Okay. Now there are two cases will be there. The first cases will be m capital M equal to small m. Next the second case is capital M is not equal to small m. So there are the two cases will be there. Now let us see the first case. When the capital M equal to small m, that means what is that infimum equal to supremum. Then when it is possible, it should be constant function. Every constant function attached infimum and supremum should be equal. So here m equal to m, no. So f is a constant function. If f is a constant function, then automatically the derivation of the constant function is 0. That means f dash of x equal to 0 for all x belongs to a comma b. So in particular for c value that f dash of c equal to 0 when the capital M is equal to small m, that means infimum equal to supremum. Now let us come to the case 2, that capital M is not equal to small m, that infimum is not equal to supremum. So already in the third condition they given f of a equal to f of b, no. Let us see here, f of a equal to f of b and the capital M is not equal to small m. From there we can write what is that, either capital M or small m are different from f of a and f of b. So from there either capital M is not equal to f of a and the small m is not equal to f of b, or small m is not equal to f of a and the small m is not equal to f of b. So when it is infimum is not equal to supremum. So let us consider, so we have these two, no. So let us consider here the capital M is not equal to f of a and capital M is not equal to f of b. Since f of c equal to f of m, no, so f of c equal to f of m, so from there m equal to f of c. So from there we can write what is that, f of c is not equal to f of a. That implies what is that, c is not equal to a. And in the same way we can prove that c is not equal to b. So here c is not equal to a and here c is not equal to b. From these two cases we can say that c is belongs to open interval a comma b. That means c is in between of a comma b. So therefore f is derivable in a comma b, that means f is derivable at c. So now we have to prove that f dash of c equal to 0. Up to now we prove that only c is belongs to a comma b, but we have to show that f dash of c equal to 0. Just now we prove that c is belongs to a comma b. Now we are going to prove that f dash of c equal to 0. Now let us see, if possible I am taking that f dash of c is greater than 0. So let then there exist one delta greater than 0 such that f of c is greater than to f of c for all x is belongs to c comma c plus delta, so that is subset of the closed interval a comma b. But we know that f of c equal to m, na, so that f dash of is greater than to m for all x is belongs to c comma c plus delta subset to that a comma b. Now from there this is contradiction. Why? Because that m is the least upper bound. So what is the least upper bound? That m is the least upper bound of f in a comma b. But here let us see, here there exists one more element that f of x is greater than to m. But m is the least upper bound, but there exists one more element that f of x in it. So this is we get the contradiction. Why we got the contradiction? We took f dash of c is greater than 0. So therefore our assume is wrong. So what is our assume? That f dash of c is greater than 0. So from there we can write that f dash of c is less than or equal to 0. Now this is next, again if possible let take f dash of c is less than 0. So previous we took f dash of is greater than 0, no. Now let us see if f dash of c is less than 0. So if f dash of c is less than 0, then there exists h greater than 0 such that f of x is greater than to f of c for all x belongs to c minus h comma c, that subset to a comma b. But we have that f of c equal to m, no. So therefore we can get f of x is less than to m for all x is belongs to c comma h comma c subset to a comma b. Now this is also we can get contradiction. Why? Because m is the least upper bound, but here again we are getting one more element that f of x is greater than to m. So this is we get contradiction. So that's why our assume is wrong. What is our assume? That f dash of c is less than 0 must should be wrong. So f dash of c is less than is wrong means that implies f dash of c is greater than or equal to 0. So from the first case that f dash of c is less than or equal to 0, and in the second case f dash of c is greater than or equal to 0. So let us see that from the first we have f dash of c is less than or equal to 0, and from 2 we have f dash of c is greater than or equal to 0. See, observe in the two cases, first one is less than or equal and the second one is greater than or equal. So what is the common point in both? That equal. So from 1 and 2 we can write what is that? F dash of c equal to 0. So this is the Rolle's theorem. So once again I will explain the statement of the Rolle's theorem. If f is continuous on closed interval a comma b and f is derivable in the open interval a comma b and f of a equal to f of b, then there exists a real number c belongs to a comma b such that f dash of c equal to 0. So this is the Rolle's theorem. So now we are going to geometrical interpretation of the Rolle's theorem. Now let us see the graph. So x axis there is the point a comma b, then this is the graph y equal to f of x. So what is the Rolle's theorem? F of a equal to f of b and in between of a comma b one element that c is exists, then the derivation of the c, that f dash of c equal to 0, and that the tangent line is there, no, the tangent line is parallel to that x axis. So, here the one thing will be there, f of a equal to f of b, and there exists one element in between of a comma b, and the derivation of the function at the point c, that f dash of c equal 0, and that the tangent line to the curve that is parallel to that x axis. So, this is the geometrical interpretation of the Rolle's theorem. So, let us see the graph. This is the graph ma. So, here see graph, on x axis a comma b is there, and in the x axis c is in between a comma b, then the f dash of c equal 0, and the tangent line is parallel to that x axis. Now, let us discuss the problems on the Rolle's theorem. So, in the exam point of view also, this is the important Rolle's theorem problems. So, is the first problem, discuss the applicability of the Rolle's theorem for the function f of x equal to x minus a whole to the power of m into x minus b whole to the power of n in closed interval a comma b, and m comma b are the positive integers. See, f is a polynomial in x. So, we know that previous every polynomial function is a continuous. So, automatically that f is a continuous in a comma b, and f of a means in place of x, if you are substituting a, that the value is going to 0, and f of b, and in the place of x if you substitute b, that is value is going to that 0. So, from the two cases we can say that f of a equal to 0 and f of b equal to 0. So, as per the Rolle's theorem condition, the condition f of a equal to f of b. Next, f dash of x. Now, let us see the derivation ma. X minus a whole power of m into x minus b whole to the power of n. So, when you are applying the UV formula, then we are getting x minus a into m minus 1 and x minus b plus x minus b into n minus 1 into x minus a. Now, let us see that x minus a into m minus 1 into x minus b into n minus 1. Let us take the common, that n plus n into x minus a n plus b m. So, we can from there we can say that f is a derivable in open interval a comma b. See, here f is continuous and f is derivable, and f of a equal to f of b. So, as per the Rolle's theorem we can applicable. So, what is the Rolle's theorem? There exists one point c in a comma b such that f dash of c equal to 0. So, when that f dash of c equal to 0, then we get c value is mb plus na by m plus n. So, in the every problem first we have to prove that f is a continuous and f is a derivable and f of a equal to f of b, then it is applicable for Rolle's theorem. So, when it is applicable for Rolle's theorem and there exists one point c belongs to a comma b such that f dash of c equal to 0. So, when you are saying the f dash of c equal 0 and we are getting the c value is mb plus na by m plus n. So, this is the first problem. Now, let us see the second one. So, examine the applicability of Rolle's theorem for the function f of x equal to 2 plus x minus 1 whole power of 2 by 3 and defined in the interval closed interval 0 comma 2. Okay. So, first f of x equal to 2 plus x minus 1 2 by 3. So, it is being the algebraic function. So, it should be always continuous. So, f is a continuous on 0 comma 2. And now, let us see the derivation. So, f of x equal 2 plus x minus 1 2 by 3, no, let us take f dash of x. So, 2 derivation is 0 and x minus 1 whole power of 2 by 3 derivation is become 2 by 3 x minus 1 2 by 3 minus 1 and 2 by 3 that x minus 1 that is become minus 1 by 3. So, when you are changing to as a numerator, that is 2 by 3 into 1 by x minus 1 whole power of 1 by 3. See, let us see that function. Here they define an interval 0 comma 2. So, 1 should be in 0 comma 2, no. So, but when you are substituting that x equal to 1 here, that become 1 minus 1 is become 0. So, 1 by 0 is become infinity. So, for here the f dash of x is not defined at the point x equal to 1. So, here f dash of x is not defined at x equal to 1 means f is not derivable at x equal to 1. So, therefore, f is not derivable open interval 0 comma 2. So, as per the condition of the Rolle's theorem, so f is not derivable. So, f is not derivable means, and f does not satisfy that all Rolle's theorem, but here f of 0 is 3 and f of 2 is 3, f of 0 equal f of 2, but it is not satisfy the second condition. So, therefore, Rolle's theorem is not applicable for the given function. So, this is the important problem. Why? Because we cannot applicable the Rolle's theorem, no. So, this type of problems in the examination they will ask. So, this is the important. So, Rolle's theorem means it should be satisfied f is continuous on closed interval a comma b, and f is derivable on open interval a comma b, and f of a equal f of b, but this problem f is not derivable. So, we can say that the Rolle's theorem we cannot applicable for the function. So, this is the Rolle's theorem. So, it is very important. And now, let us go to the one more mean values theorem, Lagrange mean values theorem. So, in the same way we have to see the statement, if a function f map a comma b to R is such that the first condition f is continuous on closed interval a comma b and f is derivable on open interval a comma b, and then there exists real number c belongs to a comma b such that f of b minus f of a equal to b minus a into f dash of c. See, observe in the Rolle's theorem also the two conditions are same, f is continuous on closed interval and f is derivable on open interval. So, in the Lagrange and Rolle's theorem, and the same two condition, f is continuous on closed interval and f is derivable on open interval. So, this is the statement of the Lagrange mean values theorem. Okay. Now, let us see the proof, and let us here define one function pi map a comma b to R by pi of x equal to f of x plus k into x for all x belongs to closed interval a comma b, where the k is a constant and is given by f of a equal to f of b. So, when you are taking that f of a equal f of b, then f of a value is f of a plus k a and f of b value is f of b plus k b. Pi of a value is become f of a plus k a and pi of b value is become f of b plus k b. From this two we can write k equal to f of b minus f of a by b minus a. So, here the important, we can define one function that pi of x equal to f of x plus kx for all x belongs to a comma b, and what is the k is a constant. How we can get the k value means that that pi of a equal to pi of b. So, from there we can get f of b minus f of a by b minus a. So, they given pi is continuous and kxb is a polynomial and it is also continuous. So, f is continuous and kx is a continuous, therefore, f plus kx is also continuous, but f plus kx means is nothing to what is that phi of x. So, therefore, phi is a continuous. See, listen one more thing, the pi is function is defined as f of x plus kx, f is continuous and kx is continuous. So, therefore, that f plus kx is also continuous, f plus kx is nothing to pi. So, pi is also continuous, and in the same way f is derivable and kx is also derivable and their sum, that means f plus kx is also derivable, f plus kx is nothing to what is that pi. So, pi is also derivable. So, therefore, phi is continuous and phi is derivable and pi of a equal to pi of b. Now, let us go to the Rolle's theorem. What is the Rolle's theorem? F is continuous and f is derivable and f of a equal to f of b, then we can applicable the Rolle's theorem, no, and here also phi is continuous and phi is derivable and pi of a equal to pi of b. So, we can applicable that Rolle's theorem. So, by the Rolle's theorem, what is that? There exists to c belongs to a comma b, then f dash of c equal to 0. See, pi dash of c equal to 0. Then what is the pi of x? Pi of x equal to f of x plus k into x. Then for pi dash of c is become what is that? F dash of c plus k equal to 0. So, when you are sending the k that side, so k equal to become minus f dash of c, but we have k value here. So, what is the k value? F of b minus f of a by b minus a. So from there we can write that what is that f dash of minus f dash of c equal to f of b minus f of a by b minus a. From there we can write f of b minus f of a equal to b minus a into f dash of c. So this is that Lagrange mean value theorem. So statement and proof both are important. What is the statement? F is continuous and f is derivable and there exists to c belongs to a comma b, f of b minus f of a equal to b minus a into f dash of c. Now let us go to see the problems on Lagrange mean values theorem. Now see, verify the Lagrange mean values theorem for the function f of x equal to x cube plus x minus 4 on the closed interval minus 1 comma 2. See, given that f of x equal to x cube plus x minus 4 is a polynomial, so every polynomial function is a continuous. Therefore f of x is a continuous and closed interval minus 1 comma 2 and f of x is the derivable of open interval minus 1 comma 2. So therefore the condition for the Lagrange mean values theorem is satisfy the given function. So Lagrange mean values theorem is satisfied, no? So what is the Lagrange mean values theorem condition? F dash of c equal to f of b minus f of a by b minus a, and that c must and should be belongs to open interval a comma b. Now let us see f of minus 1. Now here f of x equal to x cube plus x minus 4, no? Then f of minus 1 values become minus 6. So in place of x we have to substitute minus 1 and we are getting f of minus 1 value, that is 6. Next, in place of x equal to 2, f of 2, then f of 2 values we are getting that 6. Then f dash of x equal to x cube plus x minus 4, no? Then x cube derivation is become 3x square and x derivation is become 1. So this is the value of the f dash of x. Now come to f dash of c. F dash of c is what is that? F of b minus f of a by b minus a. Here b value is 2, no? That is become f of 2 minus and a value is minus 1, that is f of minus 1 by 2 minus of minus 1. That is already we find out that f of 2 is 6, f of minus 1 is minus 6. Just you have to substitute the values there and we are getting 6 minus minus 6 by 3, that is become 12 by 3. 12 by 3 equal to 4. But we have f dash of c, f dash of x equal to 3x square plus 1, then f dash of c is become 3c square plus 1. 3c square plus 1 equal to 4. From there we can write c square equal to 1. C square equal to 1 means c is plus or minus 1. So c is plus or minus 1. So out of that plus or minus 1, here only that c equal to 1 is lies in the interval minus 1 comma 2. Here that important task, what is that? Plus 1 minus 1 is there, but here minus 1 is that out of open interval minus 1 comma 2, but the plus 1 is in the interval minus 1 comma 2. So therefore we can say that the c value is 1 and therefore the Lagrange mean value theorem is verified for the function. Okay, now let us see that example 2. Find the c value of Lagrange mean values theorem for the function f of x equal to x into x minus 1, x minus 2 for all x is belongs to closed interval 0 comma 1 by 2. Now f of x equal to x into x minus 1, x minus 2 is being a polynomial condition and every polynomial function is a continuous and it is derivable. So therefore it is satisfy the Lagrange mean values theorem, no? So f is continuous and f is derivable. So as per the Lagrange mean values theorem, f dash of c equal to f of b minus f of a by b minus a. So here a equal to 0 and b equal to 1 by 2. Therefore f of 1 by 2 minus f of 0 by 1 by 2 minus 0 equal to f dash of c. So here we are getting f of 1 by 2. F of 1 by 2, how we can find out? In place of x we have to substitute 1 by 2, then we get an f of 1 by 2, that f of 1 by 2 value is 3 by 8, and f of 0 means in place of x we have to substitute 0 and we are getting f of 0 is 0 by 3 by 2, 3 by 8 minus 0 by 1 by 2 minus 0. There is nothing to what is that? We are getting f dash of c equal to 3 by 4. Now that after simplify this function and we are getting f of x equal to x cube minus 3x square plus 2x. Then f dash of x equal to 3x square minus 6x plus 2. Then f dash of c is become, just in place of x we have to substitute c, that is become 3c square minus 6c plus 2. So, from here f dash of c is 3 by 4. No? Now, we can substitute there 3c square minus 6c plus 2 equal to 3 by 4. Now, solving this quadratic equation and we are getting the two values of c, 6 plus or minus under root of 21 by 6. So, we are taking 6 plus under root of 21 by 6 or 6 minus under root of 21 by 6. So, out of these two values, only that 6 minus under root of 21 by 6 is only lies in between of 0 comma 1 by 2. Why? Because root of 21, this value is in between of 4 and 5. Why? Because root 16 is 4 and root 25 is 5. So, root 21 is almost in between of 4 and 6. So, if you are taking that 4 or whatever may be, 6 plus 4 by 10, 10 by 16, 10 by 6. So, it should be 6 minus 4, 2 by 6. So, 2 by 6 nothing to 1 by 3. So, 1 by 3 in between of 0 comma 1 by 2. But if you are taking that 6 plus under root of 21 by 6, that is become 10 by 6 approximately, 10 by 6, it is outside of the open interval 0 comma 1 by 2. So, therefore, this two condition we are taking that c equal to 6 minus under root of 21 by 6. So, this is the c values for the given function. So, this is the Rolle's mean values theorem and Lagrange mean values theorem. So, once again I will explain what is the statement of Rolle's theorem. In both cases, that f is continuous on closed interval a comma b and f is derivable on open interval a comma b. But what is the difference between Rolle's and Lagrange theorem? In Rolle's theorem, that f of a equal f of b, then there exists c belongs to a comma b, then f dash of c equal to 0. Now, let us see that Lagrange mean values theorem. So, in the Lagrange mean values theorem, what is the statement will be there? F is continuous on closed interval a comma b and f is derivable on open interval a comma b, then there exists c belongs to a comma b, then f of b minus f of a equal to b minus a into f dash of c. So, this is the difference between that Rolle's theorem and in Lagrange mean values theorem. Okay. So, it is very important when your examination points also state and prove the Rolle's theorem and state and prove the Lagrange mean values theorem. So, you need to write the statement and proof and statement and proof, and the problems, that problems are just now we discuss about the problems. No, that problems also very important. In the examination they will ask verify the Lagrange mean values theorem and verify the Rolle's mean values theorem and verify Lagrange mean values theorem and find the c value. C value is also important. Let us see in the last problem, c values we got 2, 6 plus root 21 by 6 and 6 minus root 21 by 6, but we are taking only 6 minus root 21 by 6. Why? Because that c value is must and should be in that open interval 0 comma 1 by 2. So, that is our important. Here we got two c values, but we are taking that find out that one c value. So, in the same case that previous here also plus 1 minus 1 is there, but we are taking that only plus 1. Why? Because that minus 1 is it out of this is open interval minus 1 by 2. So, this is the topic of the Lagrange mean values theorem and Rolle mean values theorem, and this is the mean values theorem. Thank you.